Hey everybody, how's it going? If you are looking for a video explaining to you how to solve linear systems of ODEs with real-valued eigenvalues, then you are in the right place. And you probably clicked the link on the document that I created. So that's great news. I'm glad you're here. I'm not going to make you wait any longer. We'll just get right into it. So today what we're going to be talking about are basically systems of differential equations. Now, remember, a differential equation is something where we define some function's derivative in terms of sort of the original function. Or in this case, we're actually, because it's a system, we get to do two functions here. These a, b, c, and d, those are meant to represent constants in this situation. So the question is, and actually a big part of Math 309 in the beginning, and frankly later on as well, is how do we deal with these things? We've done differential equations. We've done things that look maybe like y prime equals, 5y, something like that. We know how to do that. We're really good at that. We want to generalize this idea. Ideally, we'd be able to solve systems because it turns out they come up in lots of different applications. So the first thing you might think of is, well, we got a system of linear equations. Why not use linear algebra? And if you thought that, that's a great intuition about this, because that's exactly what we're going to do. If you notice here, so it's important to remember that these are functions of t. So when I say x1, really, what I really mean is this. Okay. So what we're allowed to do is we can take derivatives and whatnot. Technically, we're taking it with respect to t, but as you'll see, it doesn't really end up mattering. We just think of an abstract derivative of this function. So as you can see, we've got these constants multiplied times our functions there. So we want to see if we can write this as some vectors. So why not take some matrix A, B, C, D and multiply it times a vector x1, x2. Now let's think about this. So if we perform this matrix multiplication, we get, A times x1 sitting right here, B times x2 sitting right here, and you can see the C and the D follow exactly. So believe it or not, it looks kind of weird, but these two things are equivalent. Now the question is, what do we do over here? What is this thing? Well, intuitively, these are both vector functions, or rather, this is a vector function. It's a vector of two functions of t. We can take its derivative. So we can say that we can have this vector, which you basically just take the derivative of each component of the vector directly, and then I've got this sitting over here. So if you see, I wrote it kind of backwards here, but this is basically the exact same representation, just written slightly differently. Now, if you're a little confused at this point, you said, Jake, can come in here because I got stuck on my homework, and this is not what it looked like. Then yeah. This is not typically how we write it. Normally what we do is, since we're working with these structures, we don't want to write this kind of two-component vector every single time. So what we do is we just write something like this. These two things are equivalent. When we put this little guy on top, that means it's a vector function. So think of it as a vector. So this is equal to A, this is a matrix, A is a matrix, times our original vector function. So this is probably the form that you'll see on assignments, and they might say something like where A equals, A, B, C, D, something like this. Okay. Okay, great. So now we have this nice representation of it, but how do we solve something like this? I mean, this is still kind of a complicated issue. So I'm gonna get rid of a few things here just to clear up the clutter, and we'll get right into it. The important thing to notice is we're doing everything in linear algebra world now, so we're probably going to use some linear algebra. So let me just rewrite what we had before, something like this. So if we think back to well, I said linear algebra, now we're going to use differential equations, but we'll get there, I promise. If we think back to our differential equations days, if you remember, the thing I mentioned earlier, maybe y times 5y, what was something we knew? We know that the derivative of the function is a constant times the original function, right? And that's kind of what we have here. We have the vector derivative. Remember, everything is vectors and matrices now. So constants are, and normal functions are kind of thought of as vectors now. So basically what we've got here is we have some constant valued matrix, times a vector function. So if you think about that, that's basically still just constants times certain. And if we go back here, you can see exactly what I'm talking about. There's just all we've got are constants times our vector function, or in this case, just our two functions that we're contending with. So what that means is we can make a guess. We can make an educated guess. For example, if you have e to the 5t, and we take this derivative with respect to t, you get 5e to the 5t. So this is an example where y prime is actually equal to 5y. You see that? So we've got y sitting here, we've got the 5 sitting there. So we want to do that same thing, but of course we don't have 5s. We've got to make it general. So we guess that x of t, if you like, is equal to some constant valued vector. So this is just allowing us to multiply some constant out in front, times, oh, and the other thing is it makes it a vector, because what I'm going to do here is I'm going to multiply times e to the lambda t. Okay, so e to the lambda t is not a vector, but you can imagine if z is like a, b, and we multiply that times e to the lambda t, you can see this multiplies in, and so we kind of end up with a vector anyway. So this is the way we like to think about it. So this is our guess. Okay. Now let's just run with it. Let's see where it goes. So if we take the derivative of this, if we take this guy, this is going to equal lambda z. Remember, z is a vector, e to the lambda t. Okay, cool. Who cares? Well, I do, because let's plug it into our equation and something cool is going to happen. So we get lambda z e to the lambda t is equal to z e to the lambda t. Okay. Oh, actually, sorry. I mixed this up a little bit. I forgot our matrix. This is very important. So this is the equivalence we have. Do you see that this and this line here are the same thing if we just plug in this section? That's all of them. Okay. Now we're going to do a little algebra. We're going to cancel off these terms. And what we're left with is, I'm going to swap the order too because we're more used to seeing it that way, but I'm going to write this out. So we've got a matrix times a vector is equal to a scalar times the same vector. That sound familiar? There's a reason I chose lambda. Maybe that would ring some bells for people. But this is the definition of eigenvalues, right? An eigenvalue is when we perform a linear transformation, which can be thought of as a matrix. We multiply a matrix times something, perform a linear transformation on a vector, and all that transformation does is scale it. That's an eigenvector, and the amount it scales it by is the eigenvalue, basically. So great. So let's kind of recap here. So what we've done is we've boiled the problem down, right? Our lambda is an eigenvalue. Our z is an eigenvector. That's what we just learned, right? And that's just from the definition of those things. But what were z and lambda again? Well, remember our x of t, or rather a solution to our x of t, would be, for example, an eigenvector times e to its corresponding eigenvalue to the t. Now think about what that means. That means we boiled this problem down from this crazy system of linear differential equations to now all we're doing is finding eigenvalues and eigenvectors of A. That's all we need to do. And because of this reasoning, we get to a nice result. We get to this nice result. And then we just kind of plug it in. We can run with it. So there's one last piece, which is that you may notice that we have a 2x2 matrix. We're going to assume that the matrix is linearly independent. Or rather, the columns are linearly independent. So what that means is we're going to have two eigenvalues and two eigenvectors, right? So that means that we could potentially get two options, right? We could get, maybe this is our x1 and x2 of t. So we get maybe, and then if we add 1s and 2s to all of this, we could get two answers. Now, I can see this seeming a little suspicious, and it should. That's good. That means you're thinking about it. But remember, if you think back to your 307 days, these are both solutions to our differential equation, which remember is this. This is our differential equation. These are both solutions to it. However, what we would like is to have some kind of a general solution that would sort of encapsulate the whole behavior of it. So if these are two kind of more specific solutions or just examples of solutions, we remember there's a property from 307 that I don't want to get into right now, but basically it says that if you have any two solutions to a differential equation and you take a linear combination of those two, you will get another solution. And actually, so what that means is our general solution for x and t is going to be a linear combination. Means you can add them together and multiply them by constants, but that's all you do. So we're going to multiply by some constant, multiply our first one by some constant, and we're going to add our second one multiplied by some constant. Remember, these are vectors. If I forget the little line, just remember z is a vector when we're dealing with it right now, unless I say otherwise. So there you go. So all we've done is we've multiplied by these constants and we've added the two together. Okay. And this is our general solution. So on a homework assignment, this is what you submit. You submit this something that looks like this. Sometimes problems will give initial conditions. We'll talk about that later. If we're given initial conditions, we can actually figure out what these constants are. If we're not, then we just leave them typically as C1 and C2. So great. So I hear what you're saying, Jake. This is great, but how does it work? Well, conveniently for you, I've got an example over here. So we want our, I'm going to say where A is equal to, geez, let me think. I think we want, this should work, 3, 4, 4, -3. So do you believe me that these are linearly independent? There's no constant. We could multiply times 1 to get the other. And hopefully this will give us some nice eigenvalues. So great. So remember, we boiled the problem down to just finding eigenvalues and eigenvectors. So if you remember, there's a quick refresher here. The way we find eigenvalues is we want to take the determinant of A minus lambda I. We want to see when this equals 0. Now, this feels kind of weird. I don't really have time to get into it right now, but there's plenty of good guides on the internet for how to do find eigenvalues. I'll explain eigenvectors a little bit more, but so great. So if we do this, we get 3 minus lambda 4, and then 4 -3 minus lambda. Okay. We want to take the determinant. So this is A minus lambda I. We want to take the determinant of that. We want to see when that equals 0. So we end up getting this nice equation where we get so 3 minus, just doing determinants, so cross product basically. So minus 4 times 4 is 16. I want to know when that equals 0. So if we just FOIL this out, I believe we should get lambda squared. So we get plus 3 lambda minus 3 lambda, that cancels, and we just get minus 9 lambda, or just minus 9, sorry, minus 9 minus 16 equals 0. So 9 minus 16, that's 25. If we move that over, we get lambda squared equals 25, or more specifically, lambda can equal -5 or 5. So that was kind of quick algebra, but I hope this makes sense. I can leave it there for a moment. So now that we've got our lambdas, now we can really get into it, because now what we want to find are eigenvectors, right? So remember, the way we find eigenvectors is we literally take A minus one of our lambdas. We take this, we multiply it times a vector, and basically we want to see when that equals oh my gosh, when that well, here, let's just do it. So we take but we want to figure out what that vector is basically. So we take A minus lambda. So we take so for example we would do 3. Let's do lambda equals negative 5. We'll say this is our lambda 1. So 3 minus, so this is going to be 8, right? 3 minus negative 5, 4. And then we get 4, so minus negative 5, we add it, so 2. So what this means is, I believe it, so let me think. I think it was what I was forgetting earlier is we do a minus lambda I times z, and we want to know what this equals 0. Again, there's descriptions of why this is the case, but so we basically want to know for what vectors does this property hold. So there's a couple ways of thinking about this. The way I like to do it is write z out as some vector, and then, or actually, maybe I should do z1 and z2 so we don't confuse it with the previous ones. So basically, when you write this out, you get that 8 plus 4, or 8z1 plus 4z2 equals 0, and you know that 4z1 plus 2z2 equals 0. Okay. So basically, what we want to do is we want to find a z1 and a z2 that would satisfy this. So for example, like if we pick z2 to be negative 2 and z1 to be 1, I think that works, right? Because we get negative 8 plus 8, that's 0, and we get negative 4 plus 4, it's 0, 2. So what did I say? So then we want z1 to be 1, z2 to be negative 2. So that's our eigenvector. So we can basically represent. Now, in theory, you could have any scalar multiple of this would work too, but typically we just take a simple one, and that's kind of the eigenvector, because you can imagine if anything that's within the span of that vector would also just get scaled by linear transformation. But we just take a simple one that's nice to work with. So this is our z1. So great. So we've done all this work, but it's paid off because remember, one of our x1 here, I told you was just z1. So in this case, it's 1, negative 2, times e to the corresponding lambda, which was negative 5, t. So so what we found here, this is a solution to our linear system. Remember, we want a general solution, so we have to do this again. So if we just run through this quickly one more time, if we choose lambda to be 5, for example, and then we do we do this thing again that I forgot about briefly, but this a minus lambda I times z equals 0, then we're going to get a similar thing. So, but this time we get, for example, we get 3 minus 5. So this one is going to be negative 2. The 4 stay the same. And then negative 3 minus 5 is negative 8. So you can see it's kind of this typically happens with eigenvalues, is you get sort of mirroring images. And the whole point is it makes this matrix dependent. So anything that'll work for one line will work for the other line. That's basically what's going on here. So how do we, remember this is being multiplied times z2, this equals 0, or the 0 vector, I suppose I should say. So we get negative 2 times 4. So for example, if we use our same strategy, we can do kind of z1, z2. So for example, if we pick z1 to be 2 and z2 to be 1, I think that works. Because then we get negative 4 plus 4, and we get 8 minus 8. So that zeroes out both of them. So if we go 2, 1. That is what I said, right? Yeah. So cool. So basically now we know that our x2 of t is equal to 2, 1 e to the 5t. Okay, so now we've got our two solutions. So we know that our x of t, the general solution, is going to be just a linear combination of these. So typically we would write that like this. We go c1 times x1, which is, remember, it's just this. Pulling that straight down. And then we're going to add over some arbitrary constant times this guy right here. There you go. That's your general solution. So this is for real value. Remember, this is real value eigenvalues. We'll have a video for complex and repeated eigenvalues. Like basically the idea is what happens if you get lambda squared equals negative 25. Then you got complex numbers. what happens if you have lambda minus 1 squared equals 0? Uh-oh, now you only have one eigenvalue. So we'll talk about those cases in sequential videos. But I hope this helped a little bit. Again, I included some written descriptions if this didn't make a whole lot of sense. Hopefully some of that will. But yeah, so, thanks for watching.